Now, in the presence of O2 and CO2, heme preferentially binds to CO, forming carboxyhemoglobin, HbCO. Kf for carboxyhemoglobin is 250 times greater than the formation constant for oxyhemoglobin. Thinking about hard-soft acid-base principles, why do you think that CO would preferentially bind to hemoglobin over O2? Look at this for just a minute. When you form a bond between Fe2 plus and O2, you get a bent formation. Fe2 plus is a softer acid, whereas O2 will be fairly hard. CO, on the other hand, is a softer base than O2. It should form a stronger bond with Fe2 plus. You also have pi back bonding that can occur between Fe2 plus and CO. So those two reasons should lead you to believe that this will form a stronger bond than this. You don't have any pi back bonding in this system. Just some interesting facts that I've learned about carbon monoxide poisoning. In normal human beings, about 0.5% of your heme groups are occupied by CO. In smokers, that increases to up to 12% based upon the amount you've smoked. Now, what can carbon monoxide poisoning do to your body? Well, if 2.5% of your heme groups are carboxyhemoglobin, you could have nervous system impairment. Up to 20%, you will have headaches occur. If it goes up to 40%, you could have vomiting and dizziness. If half of your heme groups are carboxyhemoglobin, you will have collapse and pass out. Greater than 60%, you will have death. That's why it's dangerous to sit in a parked car with poor ventilation. That's how many people commit suicide when they sit in their cars in a closed garage. Next, we need to talk about iron-sulfur proteins. Now, we've talked about cellular respiration in organisms that use air, use oxygen specifically, to generate energy. When we look at iron-sulfur proteins, we're going to look at organisms that do not use oxygen. They're anaerobic. Some organisms contain proteins that contain iron-sulfur active sites that suggest that one time that the atmosphere was reducing. Iron-sulfur proteins have low molecular weights and contain high-spin Fe2 plus or Fe3 plus coordinated tetrahedrally by 4 sulfur-based donors. They are either S2- or cysteine residues. The iron centers are where the electron transfers occur. So iron-sulfur proteins are important for oxidation reduction reactions. There are 2 types of iron-sulfur proteins I will talk about: rubidoxins and ferredoxins. Rubidoxin was first isolated from Clostridium pasteuranium. This is where a single Fe2 plus is bonded to 4 sulfurs from the sulfur atoms in cysteine. The iron center is part of a protein that has 54 amino acids, so it's very small, and the molecular weight of this protein is only about 6,000 AMU. The sulfur atoms form a distorted tetrahedron around the iron center. All the bond distances are about 227 to 235 picometers in length, and the sulfur iron sulfur bond angles are between 103 and 113 degrees. The reduction potential for this cluster is about 0 volts. Rubidoxine is an important one-electron transfer site where the electron transfers at the Fe. When the Fe2 plus is oxidized to Fe3 plus, the FeS bond length shortens by 5 picometers. This is a picture of rubidoxine, but the big part that you need to notice is just right here, which is where the iron-sulfur cluster is. The iron's in the middle, and it's surrounded tetrahedrally in a distorted way by 4 cysteine residues. Now, ferredoxins are very closely related. They're found in bacteria, plants, and animals. There are actually several different types of ferredoxins. The 2Fe, 2S ferredoxins contain 2 iron centers bridged by 2 S2- ligands, like shown here. Each iron is coordinated with 2 sulfur atoms from 2 cysteine residues, shown right here. There's also 3Fe, 4S ferredoxins. They contain 3 iron centers connected by 4 S2- ligands. So here you go, 1, 2, 3 Fes connected by 1, 2, 3, 4 S2- ligands. You get a cube-like structure with one unoccupied corner right there. This cluster is held by the protein, once again by 1, 2, 3 cysteine residues. The other ferredoxin that you will see is 4Fe, 4S ferredoxin. This contains 4 irons connected by 4 S2- ligands. This ends up forming a distorted cubane structure like shown here. The 4 Fe centers are attached to the proteins once again by 4 cysteine residues. These multiple iron centers are very close to one another and end up giving a greater reduction potential than the individual irons. However, ferredoxins are still 1 electron transfer center, so even though there's 4 irons, only 1 electron is transferred, regardless of the number of irons. 1 electron transfer centers.